Hello everyone, welcome to this video. In this video we are going to learn about theory of computation, and this is also known as theory of formal languages. In this we have questions related to context-free grammar, derivation tree for sentence, production rule for Backus-naur form, and BNF, that is Backus-naur form for postfix expression. Our first question is related to the grammar. So basically grammar can be defined as a grammar contains a set of rules that can be applied to generate all strings in a language. It is a mathematical system for defining a language. In this we have grammar, by which we have two valid sentence that can be proved. First, a sentence is made up of a noun phrase followed by a verb phrase. That means we have sentence that is made up of noun phrase, and after noun phrase we have verb phrase. Second, we have a noun phrase that is made up of an article followed by an adjective followed by a noun, or a noun phrase is made up of an article followed by a noun. So these are some rules which we have given in the question. From these rules, we can form valid sentences using a series of replacements until no more rules can be used. For example, we have the quickly eat programmer is not a valid sentence because it doesn't follow the rule. We have set of terminal t equals to, in the set we have the, sleepy, happy, and etc. And other end we have set of non-terminals. In this we have noun phrase, transitive verb phrase, and etc. After this we have production rules. Production rules, as we have to check our statement that is true or false according to the production rule. First we have the happy hare runs. We are going to solve this by applying the first production rule, that is sentence given as noun phrase, intransitive verb phrase. Then noun phrase is given as apply the second production as noun phrase given as article, adjective, and noun. Again we have intransitive verb phrase. This is because the final verb run doesn't require an object. So we have used the third production rule, that is intransitive verb phrase given as intransitive verb. In this we have again article, by which we are applying the fourth production rule, that is article given as the. Then we have adjective. In this we have applied the second production rule, adjective given as happy. Then we have the noun phrase given as the happy hare runs. In this we have noun, again apply the second production rule for the noun given as noun as hare. Hence the happy hare runs is a valid sentence according to the provided grammar. Next we have the sleepy tortoise runs quickly. In this we have first sentence given as noun phrase, intransitive verb phrase by the second rule. Then we have noun phrase given as the adjective noun by the first rule for the noun phrase. Article. Article can be given as the. Choose the only rule for article. Then we have adjective given as sleepy by the production rule of desired adjective. Then we have noun given as tortoise by the production rule given for noun. Then we have intransitive verb phrase given as intransitive verb adverb. We are choosing the first rule for the intransitive verb phrase, in which we have intransitive verb given as runs and adverb given as quickly. So we can derive the complete sentence according to the grammar. In this we have third sentence, the tortoise passes the hare. We have sentence given as noun phrase, transitive verb phrase, and noun phrase given as noun phrase as article noun, and as it is from the above line, transitive verb phrase and noun phrase. Again article as it is, noun article and noun as it is, and transitive verb phrase given as transitive verb and noun phrase as it is. In this, again we have article, noun, transitive verb as it is, and noun phrase is given as article and noun. And from the values of the production rule, article gives the noun can be given as tortoise, transitive verb given as passes, article given as the, and noun given as here. So our sentence is derived completely from the given grammar. Fourth, we have the sleepy hair passes. Again, we directly apply the production rule given as sentence, noun phrase, transitive verb, phrase, noun phrase. Then we have in noun phrase, article, adjective, noun, and as it is as transitive verb phrase, noun phrase. In again, transitive verb phrase is replaced by the production rule transitive verb and as it is of the line above line. Then again we have article, adjective, noun and transitive verb as it is, and noun phrase given as article, adjective and noun. After the 6 steps we have the sentence, the sleepy hare passes the happy tortoise. In the second question we have to construct the derivation trees for the sentences in question number 1. The graphical representation of a derivation is called as a parse tree or derivation tree. So in this we have different types of nodes and left and right, and a sentence can be divided into two, noun phrase and intransitive verb phrase. Noun phrase, what in this, the internal nodes are labeled with the non terminal and represent LHS of the production rule, as noun phrase is labeled with the non terminal. And intransitive verb phrase, the children of an internal node represents the RHS of a corresponding production rule. As we can derive in this question, sentence is divided into two, noun phrase and intransitive verb phrase. Again, noun phrase is divided into three, article, adjective and noun, and this have the values the happy here. In the right hand side we have intransitive verb phrase given as intransitive verb and runs. This all derivation tree is derived according to the production rule. Second, we have the tortoise passes the hare. We have sentence divided into three, noun phrase, intransitive verb phrase and noun phrase. In the left hand side we have noun phrase divided into two, article and noun. In the middle we have intransitive verb phrase given as intransitive verb, and in the right hand side we have noun phrase given as article and noun. In the third question we have the sleepy tortoise runs quickly. We have sentence divided into LHS have noun phrase and RHS have intransitive verb phrase. Again, noun phrase is divided into three. We have article, adjective and noun, and intransitive verb phrase according to the production rule is divided into two, intransitive verb and adverb. And at last we have the fourth, the sleepy hare passes the happy tortoise. We have sentence divided into three, having left side noun phrase, middle intransitive verb phrase and the right hand noun phrase. Again the LHS noun phrase is divided into three, article, adjective and noun, intransitive verb phrase given as transitive verb and the noun phrase again given as article, adjective and noun, and we have the values according to the production rule as the sleepy hare passes the happy tortoise. Our sentence is derived from the production rules correctly. Next question we have construct a farce structure grammar that generates all signed decimal integers consisting of a sign either plus or minus, a non-negative integer and a decimal fraction that is either the empty string or a decimal point followed by a positive integer where initial zeros is an integer are allowed. For this we have terminals. The terminals can be given as a set of either plus or minus and numbers from 0 to 9. In the non-terminals we have set of sentence, sign, digit string and decimal fraction. We are going to derive the production rules as sign given as sign and integer. Again sentence given as sign, integer, decimal, positive integer. Sign can be given as either positive or negative. And again we are going to derive the integer part, that is digit. Then integer can be given as integer and digit. Then if we have digit, so we are going to derive digit as I equals to 1 to 9 including 0. Then we have positive integer given as integer and non-zero digit. We have positive integer again given as non-zero digit first, then integer, and we have positive integer given as integer and non-zero digit. Then we have positive integer given as non-zero digit also. Non-zero digit can be I, and I can be from 1 to 9 excluding 0. There is no 0 as it is non-zero digit. We our second question is, give the Backus-naur form of this grammar. Basically, what is Backus-naur form? Backus-naur form is a formal notation used to describe the syntax of a programming language and other formal languages. It is a set of derivation rules. It has a symbol, then a sign that you are going to see here. This is a symbol, this is a sign, and this fully is a expression. So symbol basically is a non-terminal variable, and sign, this sign is going to show you that symbol on the left must be replaced with the expression on the right. So for this question, our Backus-naur form can be given as sentence is a symbol, then we have symbol given as expression, sign, integer and decimal fraction. First we have sign. This rule defines the possible signs either plus or minus. Then we have digit string, that is this rules allows building a string of digits including leading zeros, comma using recursion. Then we have digit. This rule defines the individual digits allowed 0 to 9. Then we have decimal fraction, that is going to rule this rule defines the optional decimal part. It can either be empty or consist of a decimal followed by a digit string. And at last we have non-zero digit. This symbol represents any digit 1 to 9 excluding 0. So sentence can be given as sign, integer and decimal fraction. Then again sign can be positive or negative. Then integer can be given as digit. Digit can be 0 to 9 and integer again followed by a digit. Then positive integer can be given as non-zero digit separated by non-zero digit, and integer separated by integer, non-zero digit and integer. And our non-zero digit can be from 1 to 0 after excluding the 0. And we have decimal fraction given as decimal and positive integer or blank, or we can say that it is empty. In this we have the derivation tree for the question third, Backus-naur form for the signed integer and signed decimal integer. In signed integer, it is divided into two, integer and sign given as negative. Then again we have integer divided into two, digit and integer. Digit can be given as 1. Then again integer is divided into digit and digit can be 0 and integer can be given as digit by 9. In signed decimal integer we have three four parts given as sign, integer, decimal and positive integer. Sign can be given as negative, integer again divided into two, integer and digit, and integer again goes to digit, that is 3, and in this digit can be directly goes to 1, and positive integer is given as non-zero digit, that is 4. It can't be 0. Next we have question number 4. This question says that we have to give the production rules in the Backus-naur form for an identifier if it can be first one or more lowercase letter. We have to give the production rule in Backus-naur form in which one or more lowercase letters are present. So we given as identifier. This is a non-terminal, so identifier, symbol, letter separated by identifier and letter. This is one or more lowercase letter, so we have given one letter or more lowercase letter, and letter can be given as all the small letters of English alphabet from A to Z. Second, we have at least three but no more than six lowercase letters. So we give the Backus-naur form as non-terminal identifier. Then this is lowercase letter L C letter. Three LC letters are there. Then we have four LC letter. Then we have five LC letter, and we have six LC letter. This proves that our question is minimum three, at least three lowercase letter or maximum six lowercase letter, and lowercase letter are from all the small letters of English alphabet A to Z. Then again we have six question that says 1 to 6 uppercase or lowercase letter beginning with an uppercase letter. We give the answer as identifier given as UC. UC is for uppercase letter separated by uppercase letter and letter separated by uppercase letter followed by two letters again separated by uppercase letter and three letters again separated by uppercase letter and four letters again separated by uppercase letter and five letters. Letter can be given as lowercase letter or uppercase letter. Both are allowed in this. So we are going to apply both. Lowercase letters from the small character of English alphabet A to Z, small letter of English alphabet from A to Z, and uppercase capital letter of English alphabet from A to Z. Next we have identifier given as lowercase letter. In this we also have digits. So we write digitorious alphanumeric separated by lowercase letter digitorious followed by four alphanumeric values. Digitorious can be given as digit. Alphanumeric values can be letter or digit both, and letter is can be lowercase letter or uppercase letter. So we have digit from 0 to 9, uppercase letter from A to Z of capital letter English alphabet, and lowercase letter from A to Z small letter of English alphabet. Next we have question 5 that says give production rule in Backus-naur form that generate all identifier in the C programming language. In can, identifier starts with a letter or an underscore that is followed by one or more lowercase letter, uppercase letter, underscore, and digits. In this again we have identifier as the non-terminal, and on the right hand side we have the expression. And the symbol on the left must be replaced with the expression on the right. So identifier given as letter-S or separated by identifier or a symbol. This vertical bar is used to separate the values. Then we have letter-S given as letter. Then we have symbol given as letter-S and digit. Letter can be given as lowercase letter or uppercase letter. We have digit from 0 to 9, uppercase letter from A to Z, and lowercase letter also from A to Z. In question number 6, they say that give production rule in extended Backus-naur form. So basically what is Backus-naur? Extended Backus-naur form. It has additional features that enhance expressiveness and flexibility in the Backus-naur form. It is based on the foundation of Backus-naur form. So in this we have a non-negative integer, a decimal fraction that is either the empty string or a decimal point, followed by an optional positive integer, optionally preceded by some number or zeros. Here first we are going to learn about these symbols, that is question mark, this multiply sign, this question mark, this question mark. Basically, what is question mark? Question mark is used as a wildcard character within character class. It matches any single character. Okay, and for this, this is used for repetition as a repetition operator. It gives 0 or more repetitions in the production rule. So our answer can be given as numerical given as sign, a wildcard character or non-zero digit, repetitions from 0 or more, decimal again wildcard character separated by sign, 0 and decimal. Then we have sign, that is either be plus or minus, that is positive or negative. Then we have non-zero digit given as 1 to 9. In this, no zero is included. Then we have digit. Digit can be 0, so we have included 0 and non-zero digit. Then we have a decimal. Decimal can be given as decimal and digit and can be repeated 0 or more times. Next question we have question 7. Give the production rule in extended Backus-naur form for identifiers in the C programming language. It can be given as identifier given as letter symbol and a repetition operator given as, then we have letter, then we have symbol given as letter separated by vertical bar or digit, then we have letter, lowercase letter or uppercase letter. In this, lowercase letter can be given as all the small letters of English alphabet, uppercase letter can be given as all the capital letters of English alphabet, and digit can be given as 0 to 9, all digits including 0. Then we have question number 8. For each of these strings, determine whether it is generated by grammar given for postfix expression. If it is, then find the steps used to generate the string. First we have A, B, C star plus. We return as it is an expression, so we return first expression, then expression is divided in term and add operator we have. Then term is divided factor and factor. Three factors are there, and a multiply operator written as mul operator and a add operator given as identifier and mul operator and add operator. So it is generated as A identifier, B identifier, C identifier, a mul operator and a add operator. For the B, it is not generated. Then we have C. C is generated as expression, then term, then we have factor and mul operator. That is multiply operator. Then we have factor as expression, factor and multiply operator. Then we have term, add operator, factor and mul operator. Then factor, add operator, factor and mul operator, and it is given as identifier, add operator, identifier and mul operator. For the fourth, we have derived it as expression given as term, given as factor, mul operator, given as factor, expression, mul operator, given as factor, term, mul operator. Then in the next line we have factor, mul operator. Then we have factor, expression, mul operator. Then we have factor, term, add operator, mul operator and mul operator. Then we have factor, add operator, mul operator and mul operator. In the last line we have identifier and identifier, add operator or a sub operator, mul operator and mul operator. In the fifth we have expression given as term, given as factor, mul operator, given as factor, expression, mul operator, given as factor, term, add operator and mul operator, given as factor, add operator, mul operator, and at last we have identifier, add operator and mul operator. So we have generated the extended Backus-naur form. In this, we have used the Backus-naur form to describe the syntax of expression in infix notation, where the set of operator and identifier is the same as in the BNF for postfix expressions, but parentheses must be surround expressions being used as factors. For each of these strings, determine whether it is generated by the grammar for infix expressions by it or not. Basically, we have to do that we have to check this string is generated by the grammar or not. If it is, find the steps used to generate the string. If it is generated by the grammar, we have to find the steps also. So first is not generated by the grammar, we directly write it as not generated. Then second is generated, so we write expression. Then in next line we have term, add operator and term. Then we have add factor, mul operator, factor, add operator, factor, mul operator, factor. Then we have identifier, mul operator, identifier, add operator, identifier, mul operator and identifier. So this is identifier, this is mul operator, this is identifier again, then this is add operator, then this is C, that is identifier, then slash. Slash is given as mul operator and D again identifier. Next we have expression given as term, given as factor, mul operator, factor. Next line we have factor, mul operator and expression, and this parenthesis, this is used for the grouping. This vertical bar, sorry. Next line we have factor, mul operator given as grouped as term, add operator and term. Then we have factor, mul operator and a group of factor, add operator and factor. Then we have identifier, mul operator, that is it is identifier, it is mul operator, it is grouping of n, that is identifier, that is add operator, and this is also an identifier. D cannot be generated by the grammar, so we directly write it as not generated. And we have E, that is given as expression, given as term by factor, mul operator, factor, again grouped in expression, then mul operator again grouped in expression. In expression we have grouping of term, add operator, term, mul operator, then grouping of term, add operator and term. Then in the grouping we have factor, add operator, factor, mul operator and grouping of factor, add operator, factor. At last we have identifier given as m, add operator given as plus, and again we have identifier in a group. Then we have mul operator, then we have identifier, that is p, add operator, that is minus, and identifier as q in a group. Thank you everyone for watching this video.